Welcome back. So we're thinking about drawing energy from a gradient, trying to figure out how much energy is dissipated. And in the previous vignette, we worked that out in the form of these two expressions. The first one at the top is a description of the energy release rate, the free energy release rate, due to the gradient down this concentration gradient. And then we argued that if you have a full profile made up of many of these material volume elements, you'll remember that already in the context of diffusion, I made this idea of wanting to represent continuous media by a bunch of boxes, small material volume elements, and so breaking up my one-dimensional region into these various material volume elements, that permitted us to write the total free energy dissipation in this form. Now what I want to do is I before we turn to the case of Bicklet, I want to spend a little bit of time examining the question of how much work can I extract. And in some ways this is unnecessary because you already know from the physics of PV equals NKT, or the ideal gas law, and those kinds of phenomenological treatments of pistons and weights and that kind of thing. We know the answer to this question. But the reason I want to undertake this is that I want to write it in the language of free energy minimization. And the virtue of that is that this is a general technique. For example, if I were thinking about the pulling of DNA, I would use this exact same language. And furthermore, it's important to realize, because at least for me, it was not something that would have occurred to me when I was first starting out in physics, that in fact, the physics of the ideal gas or the physics of an ideal solution or even osmotic pressure is really an entropic force. And entropic forces are an amazing thing. In the small displacement limit, they're described by Hooke's law in the same way that a spring on an airplane or car suspension would be. But you can imagine the following thought experiment, or you could do the real experiment if you wanted, which is you could take two different materials to hold on to the weight that I'm showing you in this figure. So material number one would be a piece of aluminum, and material number two would be a rubber band. And let's say that you conspired to make sure that the lengths with the weight hanging there were identical. So I walk into the room and I see the two different equal weights hanging off of these two different materials. They're stretched to the same extent. They're just sitting there. And now what you propose to me is to do an experiment in which you now heat the materials. And what will happen is that the aluminum will go down, the weight will fall, whereas the rubber, the weight will go up. And therein lies the rub, because that's really telling you that the Hooke's law spring constant for the entropic spring has a linear temperature dependence in the numerator. So think about that. That's what we would find for DNA as well. In my article, or sorry, my vignette about surprise and spectroscopy, I made this whole story about once upon a time in the original paper from Bustamante and company that pulling DNA was a dramatic thing, and I haven't changed my mind about that. But at this point, it's so routine that we can use it to calibrate our apparatuses, or whatever the word is. So okay, so at any rate, what I want to do then is I want to write the total free energy of this little world, and so what I propose to do is to say I want to write. I want to write G tot of X, and just to be clear about the situation, I'll draw it from the side here. So here's my partition like this, and I hang a weight on it, and this thing is going to it's going to move by some amount from the original equilibrium position. It's going to move by some amount x, and I'm imagining that on this side there's N L ligands, and on this side there's N R ligands for left and right. And let's imagine that that NL is larger than NR, for example. So that means that the pressure. Oh no! In fact, we want to lift the weight. So we want to imagine that NR is greater than NL. What the reason for that is that gives us a pressure differential prior to the motion. So actually, sorry, did this the wrong orientation. So this thing is going to lift by some amount x, and what I want to do is I want to write the total energy. So so what I will have is that I have let's see here. I'm sorry, I'm waffling a little bit. I don't like the issue with signs here. So I'll let x become negative if it actually is going up. So I'm going to write the potential energy of the loading device. So that's what this term is, and that's very important. It's very important, and it's one of the reasons that I wanted to do this this calculation. So that's potentially the energy of the loading device, and then I also have minus T S tot of x. So that's the entropy. S tot of x is going to be equal to KB log, and then I'm going to say omega left, which is a function of x, to the L1 power over L1 factorial, and then plus KB log of omega right, and that's a function of x to the L2 power. I'm sorry, I'm remembering how I do this in the privacy of my own thinking. So I'm going to call this L1, I'm going to call this L2. This is over L2 factorial. So the number of ligands is L1 and L2. Sorry, I'm probably, it's too late in the day and I'm maybe getting a little bit brain dead. So so now what would I want to say about omega left of x? So omega left of x is going to be equal to omega and then plus x times a divided by little v. Okay, so why do I say that? Because when the partition moves by an amount x, the volume that it will have swept out is x times a, and little v is the size of a lattice element. So that's the little element of box size, and then omega right of x is going to be omega to the minus xa over v, because the total volume is conserved, and so if this thing moves to the right, then if this moves to the right, then that's going to decrease the volume on the right, it's going to increase the volume on the left. That means it's going to increase the number of states available for the guys on the left, and it's going to decrease the number of sites available, and thus the number of states for the guys on the right. I can now use Stirling, well, if I want to, I actually don't need to, so I could actually rewrite S tot of x is equal to KB L1 log of omega left, which is omega plus xa over little v, and then plus KB L2, and then log of omega minus xa over little v, and then I'm gonna write plus terms not depending on x. And just to be concrete, i.e. Minus log of L1 factorial, right? That should have shown up because of this. But it doesn't depend on x. And I'm not going to include them because the next step here, so I have g tot of x now is equal to minus mgx, and then minus kbt L1 log of omega plus xa over little v minus kbt L2 log of omega minus xa over little v. And what do I mean by, so how do I find the terminal privilege state? So there's a few ways I can say it. Find equilibrium, and this could mean sum of forces equals 0. It could also mean minimize g of x with respect to x. Those are two perspectives that they're actually equivalent, because as whoa, oops, just not doing a good job here. Page. Okay. So, in fact, force is equal to minus dg tot by dx. So that's equivalent to minimizing g of x. So, so this will give me minus mg, and then minus kbt L1, 1 over omega plus xa over v times a over little v, and then minus kbt L2, 1 over omega minus xa over little v times a over v. And this should be equal to 0. So, so that's the condition. So let's review conceptually what we're doing and why we're doing it. I simply am trying to illustrate, I could use the ideal gas law phenomenologically, and I could just say, the sum of all the forces on the piston or on the partition is 0. And that's going to be, from the left, P1 times the area of that thing, plus the force due to the weight, which is mg, times the area. So we're talking about a pressure. No, force, sorry, just mg. So P left times A plus mg, those are both pointing this way, has got to be equal to P2 times A. So that would be an equivalent way, and it would lead to the same equation, actually. I would reason that through, and then when I get the ideal gas law, I would end up actually with exactly what we've achieved here. So, and it's good to do these things in different ways. So at this point, what happens now? Next, we would multiply by omega plus xa over little v times omega minus xa over little v. What we're trying to do is get rid of the denominator in both of those second and third terms, and that will lead us to a quadratic equation. So I think rather than grinding that algebra, let's see. Okay, yeah. So, this is my practice notes to myself. So I'm going to point things out to you. So first of all, notice that at this point, what I just wrote on the previous page is this. There is one little subtlety. You'll notice there's no minus sign here, and there's no minus sign here. And the reason for that is that when I did the chain rule on this guy, I'm going to pick up a minus a over v. Okay, that's here. So these guys now have opposite signs. So as I just claimed, when you multiply both sides or all the terms by omega v plus ax, omega v minus ax, you end up with this quadratic equation that can be rewritten as this mess. This is not going to become a homework. I'm not going to ask you to repeat my steps. I'm just trying to give you a feel for what's going on. So now I have this quadratic equation, and I can solve for x. And the upshot is this. So what I get when all the dust settles is I get a relatively complicated expression. What does the expression involve? It involves the number of ligands on the left, the number of ligands on the right, the magnitude of the weight. Of course, the thermal energy is here, and that's it. Those are the things. I mean, KBT is incidental, really. So you can see, that the difference between the two sides shows up over here. And note, we're going to take the minus root because this thing has got to actually be able to go negative. So these are my notes. Let me just go back over here and kind of conclude. So what I would do if I were you is take a look at the actual functional form of x, and the thing I would say is do it at fixed weight. Keep the weights the same, but change the number of ligands. In your case, this is case one with few ligands of difference, and this one is a larger difference in the number of ligands. And note the extent to which one can do more work in the latter case. Okay, so the reason I'm that going through all of this is I simply am trying to prepare the mind, our mind or my mind, to think about how much energy is stocked, or free energy is stocked, in the form of a gradient like the Bicoid gradient. And then I want to try to think about what Maxwell had to say in his letter to Peter Guthrie Tate, where he was talking about the origins of Maxwell's demon, or I should say the origins of what we now call Maxwell's demon. He was saying, this little being could sit there and basically by tuning the opening such that molecules only went through when they were the right velocity or the right species, he could set up a gradient, and from that would be able to do work. And I'm just trying to show you what that work means. In other words, you can literally lift a weight. That's what Maxwell had in mind by producing a temperature difference between the two sub boxes, or alternatively a concentration gradient. And so, this seems very freshman physicsy, and in some sense it is, but it's also very sophisticated from the standpoint of what kind of model we're actually thinking about. So what we'll do in the next vignette is we will look at the free energy stored in the gradient, the Bicoid gradient, and then what we'll do is we'll figure out how much it costs to maintain it in steady state.